I also want to thank all the organizers for putting this great conference together. I've had a really good time. I've learned a lot of really interesting things. Thanks again, Chris. Thank you to Edwin for reading the paper I'll be talking about and giving me lots of good feedback on that. And thanks to the rest of you for having the patience and stamina to make it to yet another talk. Okay, so everyone else has been giving a sort of outline, so I figured I should kind of do that. Today I'm going to talk about the p-Adic meta integral. So before I talk about that in particular, I'm going to give a little bit of a rundown of the classical meta integral. So some of you may not have heard of it. It's okay, it will only take a few slides. And once I have run through that story, I will introduce what the p-Adic meta integral is. And the plan is to kind of show a method that I used to figure out what it was. So we will kind of do that together for the most of the talk. And then at the very end, I will kind of summarize some properties that follow from the computation. So that is it for the summary. I think I will get started. So what we want to do for the setup in the classical situation is consider a system of n labeled point charges with random locations x1 through xn. These are in the real line. And we're going to assume that these particles are distinguished by their labels. This way I can make it so that all of the tuples in R to the n are the possible microstates, rather than all of the tuples up to ordering. So I don't want my particles to be considered identical, just so I can have a very simple microstate space here. Okay, so that is the first thing. And then I want to define on the space of all microstates an energy function. Now this can really be whatever you want, but we will pick a specific one very shortly. It can be really quite general depending on what setup you're trying to work with. So here I'm just going to call E of X the total energy for a microstate X. And this is an important assumption, but we don't need to worry too much about it. It's just a way of making sure that the energy of a microstate is allowed to fluctuate without changing the temperature of the system. So the way to make this happen is to assume the system is in thermal equilibrium with a heat reservoir. So I like to think about the real line sitting in a bathtub, so it can trade energy with the bathtub without affecting the temperature of the whole apparatus. That temperature will be capital T. And to make things work out nicely as we go forward, we're going to need to fix the Boltzmann constant that makes this ratio dimensionless. And rather than working with the temperature, we're going to work with beta, which is our inverse temperature. This will just be a bit more convenient. So this is all set up. Once you have this energy function, you get a probability distribution on the microstates. Namely, you get this one. So here we have this density function where I have raised my energy times negative beta, put that in the exponent. And then I need to integrate over all of these so-called Boltzmann factors to get what's called the partition function. And that is the normalization that makes this into a probability density. Notice I put a beta here because the density changes with beta. So you can think of this more like a family of probability densities that are parameterized by the different inverse temperatures. The intuition is that when you have low energy states, you're going to have a larger value of the exponential here, and therefore a higher probability. When you have high energy states, it's the other way around. This is a small factor. So you have low probability for high energy states. And what you'll notice is that as the temperature approaches 0, this beta, which is like a decay rate here, goes to infinity. And it makes this exponential more harsh. In other words, the high energy states are especially unlikely when the temperature is low, which is very intuitive, I think. The practical use of these probability densities is that if you want to study this system macroscopically, then you can take expectations against these probability densities, and you can watch how those expected values change with the changes in the temperature or the inverse temperature. So the point I'm trying to get at here is that it's important to understand the explicit form of the partition function if you can. So our main goal in this talk is going to be computing a particular canonical partition function. Before I get to that one, I want to show you a situation, a very close situation to mine, where it was done already. So the particular one that we're going to start with, sort of as the motivation, is the classical Mehta integral, and it's defined like this. But if you sort of reverse engineer it, you can see that all the stuff in the integrand here is really e to the minus beta times an energy for an energy that is cooked up like this. So this is the canonical partition function when the energy is a sum of n harmonic potential energies, so these quadratic things that look like this. And then there is n choose 2 log Coulomb potential energies. And this just basically says that the energy is going to increase quadratically if any particles move away from the origin. The energy will also increase logarithmically if two particles get close together. So high energy means particles are either packed together or far from the origin or both. And those are going to be the low probability states. Okay. So by the way, this is where the term log Coulomb gas comes from. So we've got this potential with the logarithm rather than a distance squared or to some other power. Okay, and it gets its name from the fact that Dyson and Mehta studied this a while back in the early 60s. They noticed that when beta equals 1, 2, or 4, that this density function actually tells you how the eigenvalues of n by n Gaussian random matrices are distributed. So in particular, when beta equals 1, this density function tells you how the eigenvalues are distributed for the Gaussian orthogonal ensemble. When beta is 2, it becomes the unitary ensemble. And when beta is 4, it's the symplectic. Now, I'm not going to get too much more into random matrix theory. I just wanted to take a moment to say where it gets its name and how it's been studied before. So working with these particular values of beta, Mehta and Dyson conjectured that this was the formula for the most general beta they could find, which is all the complex beta with sufficiently large real part. So it's not hard to see from the definition of this Mehta integral that it should converge absolutely for beta with real part this large. And you can check also that it's a holomorphic function. But the explicit formula is still not very obvious. So they did see this, but they had some trouble proving it themselves. It took about 10 more years before Bombieri found a clever application of Selberg's integral formula and actually verified that this is true for this domain of betas. So what we want to do in this talk is set up the p-Adic analog of the Mehta integral and find a similar formula as well as a convergence criteria. So for which beta does it converge absolutely? So this is all the history we're going to need. It's time to go to the p-Adic case. So now we're going to suppose that x1 through xn are in QP instead of the real line. And we need to come up with suitable replacements for the Euclidean norm on Rn, and we also need to come up with the right replacement for a measure on Rn. So in this case, our set of microstates is again these tuples, but our norm is going to be the max norm. This is the natural norm to put on Qp to the n. Natural in the sense that it will preserve, it will extend the strong triangle inequality, which Qp already has. And also, as we've seen in earlier talks, this is a good choice for normalizing the Haar measure that we're going to use. So from now on, dx stands for the Haar measure that I've normalized here, and this stands for the standard norm on Qp to the n. Once again, Zp is this closed unit ball. Some others might recognize it as the ring of p-Adic integers. Another thing we need is to figure out an analog for the harmonic potentials that we saw in the original Mehta integral. So here I'm going to decide not to pick a particular function, but just something that acts like the harmonic potentials. So I want an energy function here that's going to grow quickly as x moves away from 0, but not be too badly behaved near 0. So if you like, you can just imagine that rho is this function literally with X p-adic and these norms, the p-adic norm, or this norm, the p-adic norm. So I won't be working with a specific row from here on out, but you can choose row of absolute X sub P to be exactly this, but just with the p-adic version of the norm here, if you like. Okay, also before moving forward, notice that we do have these n choose 2 log Coulomb potentials. This is really the thing that gives us the analog of the Mehta integral, which is this. So here is the p-adic Mehta integral. And as I said, the question for the talk is, what is it? So let's try to figure out what its value is, and also try to figure out for which beta it converges absolutely. Okay, I think this is a good place for me to pause. Are there any questions out there? Okay, so let's start figuring this problem out. The first fact that's really important and really handy is that because this row depends only on this norm, you can actually do a sort of trick and use the homogeneity of the Vandermonde polynomial to pull this row, or at least the dependence on row, entirely out in front of a simpler integral. You might recognize this as the Iguza zeta function attached to the Vandermonde polynomial. So I do want to point out that this integral has been done at least in an effective way using resolution of singularities. I'm going to present a different method that allows us to keep track of things a little more explicitly. So really the goal is to compute this integral now. You'll have to work out the details here to believe this identity, but I assure you for the nice kinds of row that we're using, it does work. Okay, the second nice fact is when we do this integral at right, we can actually throw out the set of points, or the set of states rather, where two particles are on top of each other. This would be an infinite energy situation anyway, but it turns out this set of states, it's a union of hyperplanes inside of ZP to the n. You can throw it out without changing the value of this integral. So we're only going to integrate over ZP to the n minus this union of hyperplanes. So this brings me to the next question. Maybe a question I should ask before this is, why would we want to throw V naught out explicitly? Why does that help us? So what I'm going to do is pick a microstate in this set, and we're going to see what advantage it has. So here is a picture of an arbitrary microstate. Notice that it has 9 particles, so we're looking at a state that's in Z3 to the 9. And to say that it is not in V naught means that none of the particles are on top of each other, which is evident in this picture. So let's go ahead and start taking some notes on what's in this picture. I want to understand how far apart every pair of particles is. So what I'm going to do is start looking at this picture mod higher and higher powers of 3. So if we mod out by 3 to the 0 or 1, Z3 is the only coset. Everything is still the same mod 1. So we don't really learn any distinction between these particles mod 1. I'm going to keep track of the fact that they're all together still by writing this partition, which is trivial at the moment. It contains 1 through 9, all of the indices on the particles. Now if I mod out by 3, I can see that some of the particles have split up into groups. So we can see they belong to different cosets of 3Z3 here. And I have collected their indices according to which cosets they end up in. And we're going to keep repeating this process to get a finer and finer resolution of this microstate. So notice that if I mod out by 9, just by way of how I picked these, you cannot see any more distinction yet. So it just so happened that 5 and 7 stayed together, 1, 2, and 9 stayed together, and then the last 4 happened to still be together. So I didn't really learn anything new, except I am going to keep track of the fact that they were all still together with the same repeated partition here. If I mod out by 27, we do learn a little something new. This particle x6 is no longer a part of this group, and that is measured here. We mod out by 81. It looks like we do get a little bit more distinction between these particles. Mod out by 243. I happen not to learn anything new again this time, but I do repeat the same partition to keep track of this happening more than once. And then finally, when I mod out by, I guess this is 729, we can see that every particle, in particular these two, they all belong to different cosets. And so we've reached this sort of other trivial partition where it's fully refined. So the importance of working with a state that's in ZP to the n minus this set is that no matter what, for a given state, there will always be a sort of finite list of partitions here that refine from the trivial all the way down to fully refined. This will happen in a finite number of steps. So you can always extract this data of partitions from a microstate in here. Okay, and one thing I wanted to add with this ... is once they have been fully distinguished, there's no need to mod out by higher and higher powers because we already know. All right, so what did we really get from this diagram? What was the data we extracted and how are we going to use it? So what I want to repeat is that the microstate determined a pair of tuples. This first tuple, called bold pitchfork, is going to be the list of all the distinct partitions that I saw in order of refinement. So I'll repeat what they are in a moment. And then this bold n here is going to count how many times each partition appeared. So we had the trivial partition, it appeared once. That's why n naught is 1. This partition appeared twice in a row. That's why n1 is 2. This one appeared once, then this one appeared twice. And then finally, this one appeared forever after. So it's not going to have an n4. So that's why this tuple is always going to be 1 less the length of this tuple. Okay, so we've got a sequence of partitions, and we've got sort of corresponding tuple of natural numbers that goes along with it. Before I move forward, I want to note that the prime p equals 3 was not really special for this example. So I could have found very many states in Z5 to the 9, or Z7 to the 9, or Z11 to the 9, or so on, that it produced this same exact chart of data up here. So given this tuple of partitions and this tuple of natural numbers that goes with it, I could have found big sets of states in each of these spaces that determine the same exact data. But notice I did not say p equals 2. The reason that p equals 2 would not work for this particular data is notice that in order for this first partition to refine into 3 pieces, I needed those 3 cosets. I needed at least 3. So when you have p equals 2, you only have 2 cosets. You will never see states that refine into 3 things at once. However, it does not hurt to say for any p, we're going to let tau p of the pair, pitchfork and bold n, we're going to let that set be the set of all states in ZP to the 9 that determine this pair. So determine the chart of data that we've seen. Notice that if p is 2 in this particular, for this particular pair, then we would just get that tau of 2 or tau sub 2 of the pair is empty. So it's still defined, it's just not interesting when p is too small. Okay, so what is the advantage of thinking about this set that is attached to this pair? The advantage is that we can compute all of these distances explicitly for states that belong to such sets. So if this set happens not to be empty, then for every state in it, we can compute this distance explicitly. And there's kind of a bit to unpack here. I don't want you to worry too much about the explicit form of this. What's really important is that it's completely determined by the pair and nothing else. So if you know this pair and you know that X belongs to that set, then you can compute this distance for all I less than j. In particular, what this means is that any function that factors through the thing that takes the state to all of the various distances. Any function that factors through this function is constant on this set. And the value, moreover, is explicitly determined by the pair. So this is a really nice way of cutting up the domain zp to the n in such a way that any function that factors through this, the fibers will be refined by these sets. Moving back to our particular problem, we wanted to integrate this product to the beta. And what you can check by taking this formula for all of the different pairs, I and j, is that you get a nice simple product that depends on the partitions and the NLs in a very simple way. I added this equals p to the minus 29 just for fun. This shows you what you would get for the particular example I showed you before. But the general thing that's important to remember is that the integrand, or once we throw a power of beta on here, it's just this power of p times several other powers of p multiplied together, where the exponents are determined, again, explicitly by the pair pitchfork and n. So that is the first key fact. And you can guess that the next key fact is it would be nice to know the measure of this set. So it turns out we can do that too. This is a bit more of a combinatorics situation. So I'm just going to walk you through the example. What we're going to do is attach a polynomial directly to the tuple of partitions using falling factorials. So the way I want to do this is I want to work through the list of partitions one at a time to make sure it's clear where the factors of this polynomial are coming from. I've colored this blue, or light blue rather, to indicate that it splits into three things, and therefore this block in the first partition gives us a 3 right there because of the number of things it refined into. In case you're wondering, this right here is a falling factorial, which goes t minus 1 times t minus 2, because there are only two factors. 3 minus 1 is 2. I highlighted this blue because in the next level, it refines into two things. And that is where the blue 2 is coming from here. So we get another factor because of that. And this next partition, I've colored 3 of the parts because they all refine. And each of those parts refining gives us another factor. And we get one more factor because there's only one more part that refines before we're done. And so we have all of our factors, we multiply them together, and we get what I call the multiplicity polynomial attached to this, this chain of partitions. So this is the explicit one from the example that we started with. The key fact too is that the measure, well, not only the measure, but this set happens to be very nice, compact and open. It could be empty, but it's still compact and open in that case. If it's not empty, it still has this very nice form, which I want you to notice again is something, so this polynomial evaluated at p, times a product of powers of p that again are very simply determined by the sequence of partitions and the sequence of NLs. This rank here, in case you're wondering, this is the number of things in the partition minus its number of parts. So the rank of pitchfork 0 is 8, the rank of pitchfork 1 is 6, the rank of pitchfork 2 is 5, and so on. Again, I added in this explicit computation for the example that we're working with. And I want you to notice there's a really nice fact that when p equals 2, you get 0 automatically just from the falling factorial factor p minus 2 here. So this formula builds in the fact that tau p could be 0 if the prime is too small. Okay, so we know the value of our integrand on each of these sets, and we know the measure of each of these sets. So it remains to put these key facts together. To make this simple, what I want to do is define the exponent, or I will call this the exponent later, to be the sum of the rank that we saw in the exponents before, and then this other sum of size of parts choose 2. And just to remind you where these things are coming from, I'm going to run back just a second. This sum of size of parts choose 2 is coming from the integrand. And the ranks are coming from the measure. So we get this from the measure, we get this from the integrand. We will see this exponent appear in a nice place. Namely, if I look at the integral of this integrand over that particular set, then I will just get the product of the integrand and the measure, which is what's inside the sum here. And what I'm doing now is I'm summing over all of the possible ways that the partitions in Pitchfork could repeat. So what we saw before was that I think n0 was 1, and then we had n1 was 2, and then we had n2 was 1, and n3 was 2. There are many different tuples n that could have the same pitchfork. So I'm summing out all of those. And what you can think is, this is really an integral over a big collection of states that gathers in a really nice way. What you'll see when you look at what's inside here is this is just a product of geometric series. So these exponents made it into a nice spot right here. And when we sum out all of these integers, or all these possible tuples rather, we get a very explicit rational function in not only p, but p to the beta. So this is a very, I think, very simple result that we can attach to this whole collection of states. And notice that the only thing that really identifies this collection is the pitchfork here. So the punchline then is, if we can identify what all the pitchforks are and then sum over all of them, we will know the formula for this integral. Okay, so I have to define what all these pitchforks are. Fortunately, they all work kind of the same. So a tuple of partitions, pitchfork 0 through pitchfork L, that strictly refines, as we have seen in the example, from the trivial partition to the fully refined partition. We're going to call this a splitting chain of order n, if it's partitioning a block 1 through n, and length L if it takes L steps to fully refine. So the sum that we care about is a sum over all splitting chains. So I'm going to call Sn the set of all splitting chains of order n. And before I attach some things to a splitting chain, I want to point out that Sn is a finite set for any given n. And the reason for that is there are only finitely many partitions of the set 1 through n. And each one of these chains, therefore, has, you have a finite number of choices for each one. And because they must strictly refine, the length capital L is never going to be more than capital N. It's never going to equal n, actually. It's never going to be more than n minus 1. So you have a finite number of possible lengths. You have a finite number of splitting chains for each given length. So Sn is a finite set. And in the end, we will get a finite sum of these rational functions. First, let me remind you what these rational functions are in general. So attached to each splitting chain, we have a multiplicity polynomial that I showed you for that one example. It's always going to be monic, degree n minus 1, with integer coefficients. So it's pretty nice. It's built out of falling factorials in a similar way. We have a family of exponents that are defined very much the same way. These are a rank plus a sum of things choose 2 times beta. And then using these two things, we form this rational expression, which we saw an example of evaluated at t equals p before. Notice that this is, again, rational in t and t to the beta with rational coefficients. In fact, if you were to expand this out explicitly, you would see that the coefficients of the numerator and the denominator are integers. Okay, so attached to every splitting chain, we have one of these rational functions. And the theorem is that the p-adic Mehta integral converges actually for the same beta as the classical Mehta integral, which is kind of interesting, with this explicit value. So we have all that front matter that we saw from before, and then we have this finite sum of explicit rational functions that we just defined. Notice that I've evaluated them at t equals p. It's kind of interesting to note here that the dependence on p is kind of simple. We can see it appear in these places. But otherwise, these rational functions that we defined can be attached directly to the splitting chains in their own right. So we can think of doing this integral over the p-Adics as merely evaluating something at p, which I think is kind of convenient. Sort of adding to that, I want to point out, I don't have time to do all the details of this more complicated situation, but the same strategy yields a formula for integrals of this kind, where you can throw in these extra factors, and you can change the beta to be anything you like, as long as the real parts are collectively large enough. So you can also do this where QP is replaced by any non-Archimedean local field. It does not matter what its characteristic is. So that's also kind of nice. And just to add why you would want to do this integral, when you have these factors inside, if A and B are non-negative integers, then you can use this computation to find the joint moments of the diameter of the gas, the expected diameter rather, and the expected minimal particle spacing. So you can find the moments of these two quantities. And again, having the SIJs allowed to be different allows you to find the canonical partition function for gases with mixed charges. So the charges may not always be the same sign or the same value. There's kind of a lot of freedom here. Again, if the SIJs have too small of real part, then your integral won't converge. One thing I want to add here that I did not write is that the region of convergence, so if rho and A and B are all fixed, then the set of SIJs for which this integral converges absolutely does not actually depend on K, which is kind of a really interesting fact in my mind, that really you have this convergence criterion and this value that depend on K, either not at all or in a very simple way. And just to get you familiar with these rational functions, I figured I should compute a few of them.
Joe, let me ask you something.
Sure.
Can you describe the poles of the metamorphic continuation of the p-Adic Mehta integral?
So that is complicated. And that does depend on the residue field cardinality, because the poles have something like a natural log of p in the denominator.
But if you assume that the cardinality of the residue field is large, can you describe the poles of the metamorphic continuation in a geometric form?
I can in terms of splitting chains. So
that's important.
Yeah. However, I will say I can describe the candidates. And I can tell when there's some cancellation, but the general cancellation is still very hard to tell. Okay. I would have to really understand these splitting chains to figure that out. That's a great question, though. That's something that I wrote a little bit about in the paper, but I didn't reach a conclusion about what all the poles are. And yes, again, that is something that does depend on K. So the region of convergence of the integral does not, but the location of the poles generally does. Okay, so again, I want to familiarize you with these rational functions. So there's only one splitting chain of order 2. It's very simple. It just has the partition 1, 2, and then the fully refined 1, 2 side by side. That's the only one. We get one term. It looks like this. When you get up to splitting chains of order 3, there are already 4 of them, and 3 of them turn out to contribute the same rational function here. I want to point out that this is kind of by chance. The fact that all the charges are assumed to be the same, still distinguishable, but the same charge magnitude, it makes it so that all these terms have the same form. In general, when Sij is not all the same for all these xi minus xj's. These are three separate terms, but they collapse in a nice way when Sij is beta for all I and j. When we get up to n equals 4, we have 32 splitting chains of order 4. And the rational functions collect like this. Notice that some of them have kind of high multiplicity, or they appear many times. This one appears 12 times. But again, there are 32 total if you count up 12 plus 3 plus 6 and 4 and 6, and then the one more here. So what you can see is that as n increases, the number of terms in this sum, while still finite, it does grow quite fast. And I actually discovered recently that this was counted for a different reason by Lengyel back in the 80s. And I'm calling this a scary theorem because what it means is if you want to do explicit computation here, you're going to have to tangle with the fact that the number of splitting chains of order n grows like n factorial squared, which is problematic or maybe somewhat alarming, to say the least. So maybe you just want to make a graph of this function. Maybe you want to check some other properties. The good news is we have another method. It's not as clear when you get the value how to organize it. So it's not going to be nicely organized into splitting chains like the formula we saw before, but it will be more efficient. So let's set up an efficient alternative for computing this meta integral. What I'm going to do is define two auxiliary functions, f0 and f1. They're going to be identically 1 for all complex beta and all real r. And then recursively, I'm going to define fn for all n at least 2 for real part of beta sufficiently large, and still for all real numbers by this big quadratic recurrence here. So notice we've got fk times fn minus k. There is this big front factor here. Don't worry too much about what that looks like explicitly. The one thing that is important to note is that when r equals 0, we do have a removable singularity. You can use L'Hopital's rule to basically take r to 0, and you can get a value of fk or fn of 0 comma beta by filling in that singularity. So you can assume that these functions are defined for all real r, including r equals 0. And two really nice things to note. One of them is that if n and r are fixed, then fn is holomorphic in beta. So that's nice. On the other hand, if n and beta are fixed, then fn is even and smooth. So that's a nice property as well that will make another appearance in a moment. So we've got these auxiliary functions. And I just want to remind you how this integral is defined. We're going to take rho from now on to be this specific function. So if you remember, rho has the norm, the p-adic norm inside of it. And that norm is between 0 and 1, precisely when the state is in zp to the n. So with this particular rho function, Zn has this particularly nice familiar form. And we discovered when it converges. Okay, so the theorem is, this is something that Chris turned me onto and I kind of put in a slightly different form. The value of the integral can be computed efficiently with this quadratic recurrence. So all you have to do is evaluate those fn's at r equals log of p. This is a natural log. And multiply by a little bit of front matter here. And that will find you this integral in quadratic time in n. So for any fixed beta, you can compute Zn in n squared time. So that's pretty nice. It's a nice alternative if you're just trying to get a value. One really fun corollary of this is it's very easy to see that Zn extends to a smooth function of p through this formula because fn is defined and smooth for all real things that we want to put here, in particular log of p for any positive number p, Makes perfect sense to put that here and put p to this power here. So Zn extends in a nice way to a smooth function of p. It is easy to determine its limit as p goes to 1. And you can also get this nice p to p inverse functional equation. That comes straight from the evenness of Fn in its first component here. So when p is replaced by p inverse, this log becomes negated, and the evenness of Fn takes care of that. So this is a pretty straightforward consequence of the theorem above. I do want to add that this particular functional equation was already known by Iguza, Denef, Moiser. I think they figured it out probably in the late 80s. But they did it in a very different way. And I figured it was nice to mention here how easy it is to see this functional equation from this formula. Okay, so moving on from that, I want to extend to the situation where the number of particles in the gas is now allowed to change. So not only are the microstates allowed to, or rather the microstate energy is allowed to fluctuate, but the number of particles is also allowed to trade with this bathtub that the system is sitting in. And I'm not going to get too into what the fugacity is, but there is a parameter, we'll call it F, that is for us really just a bookkeeping device. We're going to use it to define the grand canonical partition function. So this plays the role of the canonical partition function in the multi-particle case. So here I'm dividing by n factorial because now we are working under the assumption that the particles are all indistinguishable. And we've got this parameter to the n. And really, I like to think of the grand canonical partition function as just a generating function for all of the canonical partition functions. Notice that it is defined for all real beta that are large enough and for all complex f. It's in fact analytic for all such f. Okay, similarly, I want to define another grand canonical partition function in the situation where the log Coulomb gas is constrained to a smaller ball. So this is the open ball or the maximal ideal in ZP. So this is very much the same setup. You would get a very similar formula for Zn circ as I got for Zn before. What I want to give you now is an interesting relationship between this grand canonical partition function and that one. So this was proven by Sinclair recently. He might be telling you more about this in a little while. It's kind of an elegant fact, but it also makes perfect sense when you think about it. So what we get is a factorization of the grand canonical partition function for ZP into p copies of the grand canonical partition function in pZP. And the reason that that makes perfect intuitive sense is ZP is really just p disjoint copies of things that look just like pZP, namely it and its cosets. So this is kind of unsurprising if you think about how ZP decomposes. Again, this is kind of what I was just saying. The log Coulomb gas in ZP can be thought of as p systems, so one in each of the cosets of pZP, that are working together. So that is kind of how I think of this equation. Okay, so Chris, how am I doing on time?
You have, well, 6 minutes until 2:50, so about 10 minutes before I have to give you the boot.
Okay. So I think I have enough time to get through another layer of very similar facts, but in the projective setting. So we'll remember that the projective line is a compact metric space with a transitive action by the projective linear group, PGL2 of ZP. There's also a unique invariant Borel probability measure. I will call that U. And there is also an invariant metric, sometimes this is called the spherical metric, which is defined in this way. And with this metric in mind, you can imagine how we would set up the canonical partition function for an n particle log Coulomb gas in the projective line. So this is the integral you would get if you follow the same sort of process that we have so far. And I'm not going to be able to discuss the details explicitly, but the abbreviated theorem is that this canonical partition, the projective one, converges absolutely for the exact same beta as the other Mehta integrals did. And it's actually a finite sum over splitting chains of order n as well. And each of the summands in this sum is again a rational function in these two values that closely resembles the rational functions we saw before. But again, the way in which they're changed it's just complicated enough that I won't have time to get into it here. Sort of analogously to what I said before, you can do the same exact procedure with QP replaced by any non-Archimedean local field that you like. And you can change the beta to be a different Sij on each of these factors here. So again, you can think about the case where the gas has charges of different values throughout. And I want to add that it converges in this more general case for precisely the same Sijs as this one did. Oops, that is a typo. That K should be, this K should be the compact or the closed unit ball in K. So whatever ZP is, or whatever the analog of ZP is in K. Either that, or we could throw in a nice rho function here. Still, the fact is that these Sijs do not depend on whether we chose P1 of K, the unit ball in K, and it also doesn't depend on what K is. So it's very interesting that the region of convergence for this integral does not depend on your choice of K. And these functions, these auxiliary functions that were defined by the quadratic recurrence, they come in to help us again if we want to get an efficient way of computing these. So the theorem here is that if the real part of beta is again sufficiently large, then we could compute Zn star with a kind of similar formula that we use to define Fn. And from this, if you remember that Fk and Fn minus k, these are invariant under the change of variables, p goes to p inverse. So the same is true for these hyperbolic cosines. So the analogous theorem here, we get this limit, which is more or less the same thing as what we saw before. But the thing that's really nice is we get this functional equation that's even simpler than the one for the non-projective version. And in some ways, this is not a surprise, right? If you go to the projective situation, there's usually some compactness that helps you. But honestly, I was able to observe this fact just from the formula above. It would be nice to know a more geometric reason that this happens with this particular function. Okay, and I have just a couple more remarks about grand canonical partition functions. So we set up the grand canonical partition function perfectly analogous with the ones we did before. We just use Zn star. And the theorem here is that Zn star also factors in a nice way into the Z circs that we saw before. Remember, Z circ is the grand canonical partition function for a log Coulomb gas in p-ZP. So notice that it's almost the same as the pth power law, except we had to change the fugacity here. And this is really just an artifact of measure normalization. So had the measure on P1 of QP been slightly changed, then that we could have kept this as just F. So I don't think of this as a very serious change. And also we have a P+1 here. And the sort of intuition here is, again, that P1 of QP can be thought of as P+1 copies of p-ZP. This is because we have p-ZP, then we have P-1 copies that make up all the other cosets. And then we have another copy of p-ZP that is a neighborhood of infinity in the projective line. So that is where the p+1 comes from here. And it's kind of nice that it works out, again, just as simply. Okay, I believe that is it. Thank you very much.
All right. Thank you, Joe, for a very interesting talk. Any questions from the audience?
Just let me make a comment. First of all, very nice talk, Joe. There are many directions in which you can continue your research. For instance, the case that you study corresponds to a particular fundamental solution of the Vladimir operator. Okay, like in the classical case, in order to construct the Hamiltonian, we use a fundamental solution. You use the log of the log of the absolute value. But there are other cases in which the fundamental solution is the absolute value raised to alpha minus n. Okay, so you can study these cases. The interesting thing is the partition function in this case is not a classical Igusa zeta function. So you have to study a new object. Okay, new quotation marks. But this is an interesting problem.
Yeah, I have thought about this a little bit, and it seems really the key fact is that that polynomial in absolute value in the integrand is down on the ground, right? It's not inside an exponential, which is really the main change in the flavor of these two kinds of.
Yeah, but probably you can use a combinatorial technique to study these new integrals.
Yeah, I think at the very least, I can use this method to write the integral, the partition function, as a series, but it does not sum in a very nice way. It still converges very nicely.
In this case, you're not gonna get a rational function.
Probably not. No.
No. I am telling you, there are not rational functions. I know that.
Yes. Okay.
This is a new object, a completely new object, but it is an interesting problem.
Other questions or comments for Joe?
Hi, Joe. Thanks for the talk.
Oh, thank
you. Maybe I'm repeating again, but what about the poles of this guy? So every TP gives a pole of your meta integral, or
let me run back a few slides and see if I can point at some things. Okay, almost there. Wait, no, I've gone too far. Yes. So this is the moment where the poles could be introduced. I mean, it's where the sort of possibility of divergence comes in. It's when we sum over all of these integrals. So in fact, each of these integrals, so each summand here, is entire in beta. So this is a very simple, this summand here is very simple. However, it's when you do the geometric summation, and that is actually what gives you the condition on the way you describe the domain of convergence is you have a condition on all these exponents being real part large enough. So what ends up happening is you get a sort of polytope, I guess I should say in the Sij case, where you have a multivariate zeta function, you get a polytope of values where it converges absolutely. And along the boundary of this polytope are where all the poles live. I don't know exactly what they are, but I know that's where they all live. And I can describe them sort of in terms of splitting chains. Or I can describe all the candidates in terms of splitting chains.
And do you have any interpretations in terms of the interactions of the particles on the column gas? Or?
That's hard to say. Are you looking for something like phase transition or?
Yeah, probably.
Sort of. I actually remember reading a paper by you and Wilson where you did this zeta functions on graphs, and it looked like the phase transition. My understanding is basically the -2/n, in this situation, where the real part has to be passed in order for this to be a valid model. But other than that, I can't really say.
Okay, thank you.
Other questions for Joe? Well, if not, let's thank Joe again, and you'll be seeing some of these ideas again. Thank you, Joe.
Thank you very much.
All right, let me start. We have about 5 minutes before the next talk, which is me, but I will get my screen.